Welcome to Shanti-Peace for Mathematics. In the previous video, we have talked regarding the Cauchy's mean value theorem. In short, it is known as CMVT, which tells you that let f be a function, f and g be a, both of them are function, which is defined on AB to R. B satisfies if they are satisfying the three conditions. The first one is f and g are continuous on closed interval AB, if they are differentiable on open interval AB, and the third one is the derivative of g dash of x is non-zero for every x is in between open interval AB. Then there exists c, it is in between AB, such that f dash of c upon g dash of c equal to f of b minus f of a upon g of b minus g of a. This was the theorem. The proof for this theorem we have discussed in the previous lecture. Here we'll dealing with certain examples based on CMVT. So let's talk the first example. The question is verify a CMVT, that is Cauchy's mean value theorem, for fx is equal to ln of x and gx is equal to 1 by x in the interval 1 to e. So one should note that here this function f and the g are continuous on closed interval 1 to e, as there is a logarithm function and this is the inverse function, and it will not contain 0, so that's why it is this interval is not containing 0, so that's g is also continuous, and f and g are differentiable on open interval 1 to e. Therefore there exists at least one c, it is in between 1 to e, such that we have f dash of c upon g dash of c is equal to f of b minus f of a upon, that b is e here, so it is f of e minus f of 1 upon g of e minus g of 1. Now what is the derivative of the function f? The f dash of x, the fx is ln of x, so f dash of x is 1 upon x, and g of x is 1 by x, so g dash of x will give me minus 1 upon x square. So hence we have this f dash of c upon g dash of c. This will gives me 1 upon c upon minus 1 upon c square equal to, we have f of e minus f of 1 upon g of e minus g of 1. But what is f of e? That is ln of e will be gives me 1. That is 1 minus ln of 1 will gives me 0. What is g of e? It is 1 upon e, and what is g of 1 is 1. And if you have simplified this side, then this will be a minus c. So you will have minus c is equal to, here you will have e upon e minus 1 minus e. So therefore finally you will have c is equal to e upon e minus 1, and this is belongs to the interval 1 to e. So therefore we can say that CMVT is verified. Now let us have another example. Verify CMVT for the function f of x is equal to x square and g of x is equal to x power 4 in the interval AB, where a and b both of them are positive real number. So first, both these functions are a polynomial function, so there is no problem with the continuity and the differentiability for this function. So here f and g are continuous on closed interval AB, and f and g are differentiable on open interval AB. And the third condition, we have to check whether this g dash of x will be non-zero order. So g dash of x will be 4x power cube, which is non-zero if a and b, both of them, are positive real numbers for every x is in interval AB. So hence it is this f and g satisfies all the conditions of CMVD. Therefore f and g satisfies all conditions of CMVD. Therefore, there exists C, it is in between AB, such that g dash of f dash of C upon g dash of C is equal to f of b minus f of a upon b minus g of b minus g of a. What was the function f here? The function f is x square. So f dash of x is 2x. The function g is x power 4. So g dash of x is 4x cube. So this will leads to 2c upon 4c cube equal to f of b, that is b square minus a square upon b power 4 minus a power 4. So this will gives you 1 upon 2c square equal to 1 upon b square plus a square, because b power 4, so b square minus a square will factorize as b square plus a square into b square minus a square. So this b square minus a square will cancel, so the quantity is left with b square plus a square. So finally c square is equal to b square plus a square upon 2, that we will. So therefore we have c is equal to square root of b square plus a square upon 2. This quantity lies in the interval AB. So hence we say that this, therefore CMVD is verified. Let's have the next example. Using CMVD shows that sin B minus sin A upon cos B minus cos A is equal to minus of cos C. If your A and B satisfying this situation, that means A, B are positive and the value of C is in between A, B. So obviously one should note that here if I have to take some function as f and some function as g, and as per the given situation it's saying that your function, so we have to define the function f and g from AB to R as f of x is equal to sin x and g of x is equal to cos x for all x is in between AB. And one should note that this f function and g function are the trigonometric function, and it is sine function and cos function, so that's why they are continuous everywhere, so in particular in this interval, and they are differentiable, so that's why it is differentiable in the open interval. So we'll still write it. Here f and g are continuous on closed interval AB and differentiable on open interval. Also, the third condition, that is g dash of x should be non-zero, but g dash of x is it? So the derivative of g dash is minus sin x, and this is non-zero if your value of x is 0 plus or minus pi plus or minus 2 pi. That means this value of b, it cannot be pi or any of this type, but because it is positive, so should not be a pi. Okay, and then we can apply this CMVT onto this. Then what we can say is here f and g are satisfies all the conditions of CMVT. Therefore, there exists at least one C in between AB such that f dash of C upon G dash of C is equal to f of B minus f of A upon G of B minus G of A. But what is f function? The function f is sin x and the function g is cos x. The derivative of sin x, we know it is cos x, so it is cos c upon cos sin c minus sin c, because the derivative of cos is minus sin. That is equal to f of b, that is sin b minus sin a upon cos b minus cos a. And this quantity is minus cot c, and that is exactly the things which we need to prove. So let's solve now next example. The next example is to discuss this, so that this inequality if the x is between 0 and 1. And from this middle expression you just see that I can say it is ln of 1 plus x minus 0 and sine inverse of x minus 0. So this has to be ln of 1 and this is sine inverse of 1. So it will suggest that we have to define two functions which is in this fashion. The function f is ln of 1 plus x and the function g is sine inverse of x. So let us define the function f and g, and both of them has to be defined over the some interval 0 to 1. Or if I can say 0 to x, where your x is between 0 and 1. So for any x which is in between 0 and 1, we will define this to R as f of x is equal to ln of 1 plus x, g of x is sine inverse of x. Now first one should note that this here f and g are continuous on the interval 0 to 1, or I can say 0 to x, and they are differentiable on the same interval, open interval 0 to x. Now we have to check whether the derivative of g is non-zero. The derivative of g is, that means sine inverse of x is 1 upon 1 minus x square. So we have g dash of x which is 1 upon 1 minus x square, which is always non-zero for any x between 0 and 1. So that means this f and g satisfies all the conditions of CMVT. Since they are satisfying the conditions of CMVT, we can say that there exists at least one C in between 0 to x such that f dash of C upon g dash of C equal to f of x minus f of 0 upon g of x minus g of 0 we call. Now let us see what is this expression we have. As we have f function which is ln of 1 plus x, the derivative of this one is 1 upon 1 plus x. G of x is sine inverse of x. The derivative of sine inverse of x, as we may have did it earlier, it is 1 minus 1 on x square. So from 1, what is the expression 1 we have? You just see that this is one expression. f dash of c upon g dash of c. So f dash of c is 1 upon 1 plus c, and this is 1 upon square root of 1 minus c square. That is equal to, here it is fx. Fx is ln of 1 plus x minus ln of 1 upon sine inverse of x, that is g of x, minus sine inverse of 0. Now if you simplify this one, that is 1 minus c square will simplify as 1 minus c into 1 plus c. So 1 square root will get cancelled out, so it will left with square root of 1 minus c upon 1 plus c, because this is denominator goes in the numerator, and 1 minus c is cancelled out, so one of them, so square root is left, and this one is ln of x, 1 plus x upon sine inverse of x. This is our expression that we are looking for here in between, and here the value of c, which is in between 0 to x. So what we have here is 0 less than c less than x less than 1, because x is less than 1 we have. So what will be the 1 minus c upon 1 plus c? The 1 minus c upon 1 plus c is greater than 1 minus x upon 1 plus x. That obviously we can say. And so that will be greater than 1 minus 1 upon 1 plus 1 due to this. And so this will imply is 1 minus c upon 1 plus c is greater than 1 minus x upon 1 plus x, which is greater than 0. So this will imply the square root of 1 minus c upon 1 plus c is greater than square root of 1 minus x upon 1 plus x. So you just observe that here we have this quantity, and we have shown that that quantity is greater than this quantity, which is greater than 0. If I call this is the first equation. So what we got now, and how we achieve this one, that also I can tell you how we achieve this one. See, here we have this expression, so that's why this will give me 1 upon c is greater than 1 upon x, which will be greater than 1. Due to the, if I take the reciprocal, the inequality will be changed, and then you apply the dividendo component rule here. So if you apply the dividendo component rule, will gives me 1 minus c upon 1 plus c is greater than 1 minus x upon 1 plus x greater than 1 minus 1 upon 1 plus x, 1 plus 1. So this is the rule which we have applied here. So that's why we got this expression. And hence what we get from this one and from this expression, so from 1 and 2, what we can say is square root of 1 minus x upon 1 plus x, which will be less than 1 minus c upon 1 plus c, which is equal to ln of 1 plus x upon sine inverse of x, which will be less than 1. Now let us have next example. Using CMDT, prove that this expression. Now here the question is how you can take out your function as f function and the another one is g function. So doing the some rough work, this expression is 0 less than ln e power x minus 1 upon x is less than x. So if I multiply x, because x is positive, so inequality will not be changed, we'll have this. And if I take the e power, that is e power 0, the ln of e power 0 will give me the same thing upon x is less than e power x. And this will suggest that you have to take here, that is e power x, right? This 1 I will take it as e power 0, and x minus 0 if I can do. So this is my function f and this is my function g. So this will suggest that what the function you have to take. So let us define the function f and g from 0 to x to r as fx is equal to e power x and g of x is equal to x. Here f and g are continuous on the interval 0 to x where x is positive, and they are differentiable on this open interval 0 to x. Also, this z dash of x is 1, which is non-zero for every x. Therefore, this f and g satisfies all the conditions of CM. Therefore, there exists at least one c in between 0 to x such that f dash of c upon g dash of c is equal to f of x minus f of 0 upon g of x minus g of 0. What is the function f? We have considered it is e power x and g of x is x. So that's why the derivative of f of x is e power x, that is e power c upon the derivative of g is 1. That is equal to, what will be the fx is e power x, e power 0 upon x minus 0. So finally this will simplify it as e power x minus 1 upon x, that is e power c. Now your c is in between these two, that means your c is between 0 to x. So I will start with this, and how to make out this expression e power c. So I will take the power, e power 0 is less than e power c is less than e power x. So that's why this will give me 1 is less than e power c is less than e power x. But value of e power c, you have this, so we'll substitute that over here. That is 1 is less than e power x minus 1 upon x less than e power x. Since I have to prove this expression of this type, so for that I will take ln. So that is ln of 1 is less than ln of e power x minus 1 upon x is less than ln of e power x. So therefore this will give me the ln of 1, we know it is 0, so it is 0 is less than ln of e power x minus 1 upon x is less than x. And to divide x, this will give me 0 is less than 1 upon x, ln of e power x minus 1 upon x is less than 1. Hence we achieve what we want into this expression. So that completes by proving this CMVT and also with this lecture. So if you have any comments, please do it in the below. If you like this video, please press the like button. Thank you very much for listening me. See you in next video. Till then, bye bye. Ciao.